a lot of this review has to do with what we're about to cover today. And I know most of you have done quadratic equations quite a bit. And as you know, sometimes to solve quadratic equations, you factor and set the equation equal to 0 and factor to get your answer, one of the strategies. So that's why we had this little preview exercise on factoring. A lot of times we have to work with radicals, as you can see, because the quadratic formula has radicals in it, and sometimes you're asked to simplify. Now, one of the things I want to point out, because I happen to notice this particular problem has a perfect square, the square root of 121. If the number that's called the discriminant, this piece under the radical, b squared minus 4ac, is called a discriminant. If that number is not a perfect square, I'm never going to ask you to put it into your calculator and give me an approximate answer, because we're always looking for the exact solutions for equations. So do not put, if it's not a nice perfect square, then you can either simplify it like you did up here and reduce your fraction, or if it's not a radical that can be simplified in any way, to keep your answer like that, like it would be. For example, if you had something like this, I'm just making this up. If we're solving an equation, this isn't an equation right here, but if you had the solution that perhaps looks something like this, you would just leave it like that. Those are your two answers, -7 plus the square root of 5 over 2. And if you literally substituted that back into your original equation for x, you would get the left side equaling the right side. So I don't ever want you to put this in your calculator and then put equals an answer, because that's not correct, because it would be an approximation. You'd have to use these little, anytime you give a decimal value for a radical that, like square root of 5, you never use an equal sign, because it's irrational. There's no exact answer. It goes on, the decimals go on forever without a pattern, and they never stop. So this is always a symbol you'd want to use. Okay. You might see that on your quiz when I get it back. I didn't take off if you tried to combine those two like radicals and they weren't the same. But I did point out this to you, that these are the little squiggle marks that you use for approximate. Okay, so I'm sure a lot of you, when you saw, if you looked ahead, you looked at today's topic, but I love this cartoon with the square root of -1 on the psychiatrist's couch saying, "Do I really exist?" I thought that was kind of clever. Yeah, it is funny. Anyway, I just wanted to, before we get into defining the square root of -1, what's lost along the way in our math education is that this thing, whether it's the square root of -1 or even just the use of a radical symbol, hasn't always existed. All of what we take for granted today, whether that be just even algebra, even basic algebra, had to be written and discovered and imagined at some point in our history. You know, it wasn't handed down to us as a civilization along the way. So what I wanted to show you is the University of, the Westfield University received a grant. And I know some of you are going to say, no way would I ever be interested in this. But they have a series of booklets about just about everything in mathematics. As you can see from, this one is really interesting. If you noticed on our Moodle site, there's a knot that I have on our Moodle site, and it came from this group. And there's a whole knot theory booklet about knots, and you know, music, the math of music. And then there's number theory and patterns and the infinite, you know. But this book here, Truth, Reasoning, Certainty, and Proof, if I turn to page 21, they have a whole, I think it's about 30 pages long or 20 something pages, a whole chapter on the square root of -1. And what's really interesting, I know you don't think maybe that this could be interesting, is, and this is what I'm asking you to do, to think about this. I'm just going to read this to you. We have added this character to the mix of our everyday arithmetic simply to explore what might happen, the character being the square root of -1. This is a work of imagination, just as the creation of a character in literature, a compositional theme in a painting, etc. Samuel Taylor Coleridge, you might recognize him from your literature class, coined the term suspension of belief, which he thought was central to an audience's ability to imagine the often illusion setting of poetry, theater, and literature. If you are troubled by our new character, try to suspend disbelief and give this new character a chance, introducing the imaginary unit I, which is equal to the square root of -1. Now, if you're at all interested, I'm just going to boot up here to, I think it's 28 or 29, because I find the history of this thing really interesting, especially when mathematicians were sort of stealing from each other. So in this chapter, expanding our notion of numbers via solving equations, they go into the history. Now look at these dates, 1465 to 1526. There was these three mathematicians they used to have these like contests to solve equations. And it was in one of these competitions that they came up with the square root of -1 being I. Now, the actual problem that this guy solved, actually Cardano, who's given all the credit, he came up with a formula for a cubic equation, just like we have a quadratic formula for second degree equations. He came up, and I used to give it to my students to watch their face. It literally would take like this, almost this whole page here. He came up, well, he gets the credit, but it was really another man that came up with the formula for solving a cubic. And it was actually this equation right here where they use the character I, which equals the square root of -1. So it's part of someone's imagination. So you're never going to feel the square root of -1 in you're not going to feel it as a concrete object like you may our number system, adding things or subtracting things. You can feel that, you can do that. You'll never feel this thing. So you have to, as Coleridge said, suspend disbelief and just work with this like you would work with any numerical quantity in mathematics. You can apply adding and subtracting to this thing, multiplication and division. It's just a character. So this is the definition that you need. The square root of -1 is I. And then if you happen to have something other than 1, notice how we can simplify this. If we have the square root of negative some number, k, then you separate it just like we've been doing with things like this up here, square root of 18 and square root of 8. You separate it by factoring out the square root of -1 and then the square root of k. And then the square root of -1 is given the symbol I. And then you have square root of k. Now, if k is a number like 9, we're golden. We can simplify that. If not, we can simplify it. So let's see how we would evaluate the following. If we were asked to find the square root of -49, we know there is no real number that we can square to get -49. So this is where the imaginary unit comes in. And this whole other field of numbers called complex numbers. So we know if we're dealing with real numbers, the answer to this would be no real number exists. However, we're expanding our sort of view of the mathematical world now and including this imaginary unit. I don't even know if I'm recording. I am? Good. Okay. So the square root of -49 you can write like this. It's the square root of -1 times the square root of 49. And then we say the square root of -1 is called this character I, and the square root of 49 is 7. So you can write it as I times 7 or 7I. Now typically when the square root, the number under the square root is a perfect square, we tend to put the answer in front of I. When it isn't, we put it to the right of I, and I'll show you why that happens. So let's take a look at square root of -8. Anybody want to help me with starting this, how I might start it? Square root of -1, square root of 8. Now look up to your preview exercise, your first preview exercise. You've already simplified the square root of 8 to be 2 square roots of 2. So this is I, Square root of 8 is 2 square roots of 2. So if you were to simplify that, this is just all multiplication. It doesn't matter the order, but typically we write it like this: 2 times I times the square root of 2. Okay? And the reason we don't put the I after this is we don't want to confuse that none of this, the 2 or the I, is under the radical anymore. Okay, yep, Lucas? Yes, because there's no negatives anywhere. The square root of 8 doesn't have a negative attached to it. And then the square root of negative 1 is the I. Yeah, so there's no negative here once you simplify it. Okay? Now, just like we can do with any number, we can take I and we can apply various powers to it. So if I were to square I would be squaring this. And anytime I square a square root, these two things undo each other. They're inverse operations, and I get negative 1. So this is negative 1. So let's play this game. What would happen if I cubed I square? Well, cubing it would be this: I squared times I to the first power. So I square we just discovered is negative 1. So this would be negative I. And if I raise it to the fourth power, I get I squared times I square, which is negative 1 times negative 1, which is 1. So you can just keep playing this game. These are the only 4 possible answers for any power of I, because once you get I to the 5th, you get I to the 4th, which is 1 times I. So you're right back here to where you started. So those are the only 4 possible answers for any power of I. It's either I is the square root of negative 1. It's either going to be simplified to negative 1, negative I, or 1. Okay? In our course, this is really what we're going to be mainly focused on, is that I squared is equal to negative 1. That's what comes up most often when we're solving the problems we're going to be looking at today. Okay. 3, if a radicand is negative, we write the radical in terms of I before performing any operation. So we had just seen earlier that you could take something like the square root of 3 times the square root of 5 and call it the square root of 15. We don't do that here, because if we multiplied these two things, we'd get the square root of positive 100. And this is not equal to the square root of 100. So when you have negative radicands, you actually solve each of these, or simplify them, not solving, this is not an equation. You simplify each one of them individually. So what I did is I just split up the square root of negative 20. Maybe I lied to you, but you'll see why I didn't lie to you. Or maybe I did lie to you. Square up the square root of negative 20 into the square root of negative 1 times the square root of 20. And the square root of negative 5 is the square root of negative 1 times the square root of 5. So this is I times the square root of 5. Square root of negative 1 is I, square root of 5 is square root of 5. This square root of negative 1 is also an I. So the square root of 20, if we go off on the side of our paper, is the square root of 4 times 5, which is the square root of 4 times the square root of 5, which is 2 square roots of 5. So now we got 2 square roots of 5. So now we've got one huge long multiplication problem. And so let's just reorder things. We have I times I, we have a lonely 2, and then we have square root of 5 times square root of 5. So that's the same as I square times 2 times the square root of 5 square. So let's simplify this. We just saw that square root of, I square is negative 1. So this becomes negative 1 times 2. And then the square root of 5 squared is just a 5. So notice our answer is negative 10. So this is why we can't multiply these two things and get 100 and say our answer is 10. Because the positive square root of 100 is 10. This symbol says, would it be asking you for 10? And our answer is negative 10. Okay? So this is, you'll have a little work, some of you probably are more familiar with working with I and doing arithmetic with it. You'll have lots of practice today. So any questions before I move on any of these steps? Anything at all that you can put into words? All right, so let's take a look at the next page. So quadratic equations, all of this happens because we have to learn some strategies for solving quadratic equations. And we call linear equations first degree equations. And that this term first degree comes from this idea that the highest power that we see the variable raised to is the first power. That's how we recognize a linear equation. So we call quadratic equations second degree equations. So here's some examples of quadratic equations. So the general quadratic form for an equation is, this is what we call the general form. Neither of these equations have been put into this form. What we do with quadratic equations is we put all of the terms on one side of the equation and we set the other side equal to 0. So since we can have up to 3 terms, notice we use the first 3 letters of the alphabet. A is the coefficient of your x squared term, B is the coefficient of x, and then C is your constant. Now sometimes we may have all of these terms present and sometimes we may not. Of course, A cannot equal 0, because if A was 0, then this would not be a quadratic equation anymore. It would be linear, because 0 times x squared is 0. So it's possible for B to be 0 and it's possible for C to be 0. So you could get a quadratic equation that looked like this. Okay, and in this case, C would be 0. You could get a quadratic equation that looks like this. In this case, if you put everything all on one side of the equation, notice your middle term is missing, the bx. So C and B can be 0, and sometimes you have an equation with all 3 terms present, but A always has to be a real number. So let's take a look at some of the techniques. Now, what does that say? Oh, I see or. Okay. So the first technique is when we have the B coefficient is equal to 0. So these types of equation is where B equals 0. So you might see something like this. Ax squared equals the constant, where you start off with something square equals a constant. Sometimes it's all on one side of the equation, like this. And sometimes it's just a bunch of stuff like up here. So this still looks like this, except for what you're squaring is actually a binomial instead of a single variable. So anytime you see some number times something, I call it stuff here, square equals a constant, there's a particular way to solve this equation. Okay, so let's take a look at solving x squared equals negative 25. Now I've already done my song and dance on this to you when we talked earlier about when you have a square on one side and a number on the other, the tendency is you forget that there's 2 answers. Okay, there's always 2 answers to a quadratic equation like this unless it says x squared equals 0. That's the only time you get one answer, 0. 0 doesn't have an opposite, right? So when you see something like this, you have to remind yourself that there's 2 answers to this equation. And the minute you see x squared equal to negative 25, you know that those answers are not going to be real numbers. So you have a choice, and this is what I would recommend. I would recommend putting this quadratic in standard form, which is get all of your terms on one side of the equation and set it equal to 0. So this is what I would do. Now you might say, if that said x squared, so here's a little side note. If that said x squared minus 25 equals 0, I'd be golden because I know I can factor that really easily. I love these things to factor, the difference between 2 perfect squares. It's just x and x, 5 and 5, plus and minus, and you're all set. However, this is not the difference of perfect squares, it's the sum. And you've been taught you can't factor this. This is prime. However, that's using real numbers. We can now factor this, and let me show you how to do it. It's set up the same way as this sideshow. You do the same thing. You set up your little parentheses like this, and you do x and x. You do your plus and your minus. But instead of putting just a 5 in each of these second positions, you put 5i. What? Well, let's see how this works. So let's see. We know we factor something correctly if, when we multiply it, we come back to where we started. So let's see. The x times the x gives you x squared. 5ix is your middle term. So I'm just going to write it just like I see it, 5i times x. My outer term is negative 5ix. And then I get this thing. The signs are different, so I have a subtraction, and I get 5 times 5, which is 25, and I times I, which is I squared. Well, just like this multiplication over here, if I checked it, you always lose your middle term. Those will always be opposites, like that. So now what are you left with? X squared minus 25I squared equals 0. And remember, what was I squared equal to? Negative 1. So look what happens. You replace that I squared with negative 1, and you get x squared plus 25. Okay? So you're right back to where you started. So all I'm trying to do is encourage you not to be flipped out if you're trying to factor this. You do it as you normally would, as if there was a subtraction there, but you just put 5i instead of 5 and 5. So now when you solve this quadratic equation, you set each factor equal to 0, and you have both of your answers. You'll never miss one of your answers. So you set these two factors equal to 0, and you get x equals negative 5i here, which is one of your answers, and x equals positive 5i there, which is your other answer. So when you factor, you automatically get both of your answers. It's only when you try to take the square root of both sides that you get into trouble if you forget the plus and minus. I remember the first time we looked at one of these earlier, Haley bailed us out and said plus or minus. So she clearly, wasn't it you, Haley, that said the plus and minus that day? You don't remember, but I do. So what I'm trying to have you avoid is this kind of thing. This is what I'm trying to have you avoid. And as you know, erroneously, you do this instead of doing this. And then you go like this. You'd go 5i. So you miss one of your solutions. But what it really is the absolute value of x is 5i, which means you can have either a 5i in there or a negative 5i in there. So you have two solutions. Yeah, if you do that, then that's okay. But I've seen 70% of students miss it. You know, it just is something that, you know, once you do this and you write x, your tendency is only to do one answer. So this will guarantee that you never forget that. Okay? So this again will take some practice if you haven't done a lot of work with imaginary units. Okay, so this idea that I just showed you uses this property for solving this strategy and property for solving quadratic equations. If you have two things that you multiply that equals 0, you know one of them has to be a 0 for the answer to be 0, for the product to be 0, or both. A equals B. So here's a situation where we can solve a quadratic equation by factoring. So the first step here is to do what? I'll be the writer. You tell me what to do. Set it equal to 0, right? Set the equation equal to 0. And how do I do that? Someone else? Add 20 by adding 24 to both sides, right? So let's do that as the first step. Okay, so we have plus 24 to both sides. So we get x squared plus 11x plus 24 equals 0. Okay, so here's where, the picky math teacher comes in. Here's an equation. Do you all agree that this is an equation? The very first thing there. When you solve an equation, everything that comes below that, if you go down your page, is an equation. You don't drop off part of it. So often what happens is students forget the equal zero part. You always solve an equation by making it a more simplified equivalent equation. In this case, by factoring it, it doesn't matter whether it's an addition problem on the left side of factoring. However, the factoring properties is what helps us to solve it. So you have to carry this idea of an equation all the way down as you solve this. So in this case, I want to find the factors of 24 that add up to 11. And what are the factors of 24 that add up to the number 11? 8 and 3, right? So I factor this, x plus 8 times x plus 3. And please make a little note to yourself that if this is your habit, you have to change it. You don't now say x plus 8 equals 0, because you have now just written an expression. You have to say equals 0. And this is how you now solve it. You set each factor equal to 0, and here are your two answers. Okay. So sometimes factoring, when it's something nice like this, is very quick. If it's a monster to factor, then you're not going to use this strategy. So what I'm trying to do is introduce to you flexibility. You have more than one way to solve a lot of these quadratic equations. Now, some people say, well, I just use a quadratic formula. And I say, that's fine, as long as you can use it properly. Some students rely on the quadratic formula, and they just mess it up to no end. So you should have something else in your pockets, a little tool to either check yourself, or if you are not good with simplifying radicals like we did on this backboard, you have some other way of doing it. So I have your little note there, and then unfortunately today is a little longer lecture than our other days. The third method, which is the quadratic formula, can be used no matter what your equation looks like. It will work all the time, whereas factoring only works for certain equations. And the extraction of roots, which I'm trying to get you not to use, can only be used for certain equations. However, this formula, notice, this is an equation. When you end up with your final answers, your final equation, just like when you solve a linear equation, you keep solving it and then you get x equals a number. You end up with, this is the answer no matter what the original equation is. And this was a huge discovery. And as I said, there is a formula for when it's a cubic as well, called Cardano's formula. So let's take a look at this, and let's kind of talk about some of the areas here that we can sort of areas where we could make a little mistake, so I can try to make you aware of it. So it says, solve this equation with a quadratic formula. And James asked this earlier, list your solution set using the roster method. So back here, when I did this equation right here, this is how we're used to writing it. But for my math lab, they want you to write a solution set. And I've mentioned this a couple of times. So when you write a solution set, they also want you to put the smaller number first. So the smaller number out of these two is the -8. So you would put that first and then the -3, and then your larger number. Okay? Just so that you know how to enter your answers in your homework. So they'll probably, on my math lab, they have these little curly braces, and then they have two dotted rectangles in there for you to put your answer in. All right. So let's take a look at this. If I were to do this problem, I would factor it. I wouldn't even think about it, because I'd say to myself, factors of 7 that differ by 6, 7 and 1, and I've got my problem almost done. That's how I would do it. Because I can factor this, I know it's going to come out. My radical, my discriminant is going to be a nice number because I can factor it. Anytime you can factor something, you always get rational answers, rational numbers for your answers. You won't get square roots of 5s or square roots of 17, anything like that. So However, to have practice with the quadratic formula, how well do you do with memorizing stuff in general as a person? Pretty good? Not so good? Yeah? All right. So why is it that when we're young, we can